Let's now do this problem where we do a much more complicated flux calculation. So calculate the flux of the field given by this, so it's a vector field, through the outer surface of the cylinder with radius r and set values between 0 and h. Consider only the curved surface, not the caps. Okay? So what is being asked? We are being asked to imagine we have a cylinder of radius r and height between z equals 0 and z equals h. So the height is h. And we are being asked to calculate the flow of this vector field. And I don't know how this vector looks like. It seems to be a very complicated vector field. Okay, so you can imagine, I really don't know how this looks like. It's a crazy vector field. Yeah. And we are asked to calculate the flux of this vector field across the curved surface of the cylinder. So only this surface here, the curved one. Okay. We are not calculating the flux on the top cap or on the bottom cap. Okay. So how do we do that? Let's write what we want to do. We want f dot ds. This is the calculation of the flux. So let's do this calculation, where f is this vector field, which let me write it as a column. It's yz times x hat, then xz times y hat, and then xy times z hat. Okay, it's a very complicated vector field, which might be the flow, something describing the flow of something, or it might be a magnetic field, or whatever it is. Yeah, and S is just this surface here. So step number 1, we parameterize the surface. Okay, so we have parameterized the surface of a cylinder many times now, so I'm going to directly write it. We'll have two parameters that allow us to move throughout the surface, and those two parameters will be the azimuthal angle phi and the z axis and the z parameter. So then we will have our surface as r cosine phi, r sine phi, and z. Okay, so those will be, basically I used cylindrical coordinates and I fixed rho equals r, so that we have a fixed cylinder. Okay, and the limits of our parameters are phi goes from 0 to 2 pi and z goes from 0 to h. So that's step 1. Step 2 is to find ds. Now I am going to look it up. So look it up. So let me look it up on the table. So this is our table. So we are in cylindrical coordinates and we fixed rho equals r such that d rho will go to 0. So we are left without these two. So the only term that is left is rho d phi dz times e rho hat. So this is going to be our ds. Okay, so let me copy it down. So ds vector is going to be rho dz d phi. Sorry, rho is equal to r, right? Because we substituted rho equals r, so it's going to be r dz d phi in the direction e rho. Okay. Now, could you have found it by geometrical intuition? Well, of course, you can always find it by geometrical intuition. So if you have the surface of the cylinder here, so you select a small ds where you increase z by an amount dz as usual, and you increase the angle by an amount d phi. So this arc is r times d phi. So you know that the size of this area is r d phi dz, but what's the direction? Well, that's more or less obvious. So the direction is pointing away from the z-axis. So this is e rho hat, right? Because this is the z-axis here. Okay, so it makes perfect sense. You have r dz d phi in the direction of e rho hat. Okay, so we found ds, and we are happy that ds makes sense. Third step is evaluate the integrand at the surface. And this is the step where this problem might become a bit messy. So I predict it could become messy because our integrand has plenty of x, y, and z, and also the direction, it is a vector in the three directions, x, y, x hat, y hat, z hat, while our ds is on the e rho hat direction, and we're going to need to do a dot product there, okay? So let's write it explicitly. So our integrand is what is inside of the integral. So it's f dot ds. So f dot ds. I always draw the dots very big so that you don't forget, yeah? So f is our function. So let me write it explicitly. It's yz in the x hat direction plus xz in the y hat direction plus xy in the z hat direction. Dot ds, which is r dz d phi in the e rho direction. So now we have to decide, do we first substitute x, y, and z with the appropriate x, y, and z given by the parameterization of the surface? So we can substitute x equals this, y equals this, z equals this. But we also have to do the dot product. So in this case, let me do the dot product first, okay? The order doesn't matter. But let me do the dot product first. How do I do the dot product between this rectangular basis and this cylindrical basis? So then we seem to have a problem, right? So what we can do is we can write the e rho hat unit vector in rectangular basis. And in order to do this, this is an equation that is given to you in the exam, all of the unit vectors. So I have it in kits in the reference list of equations, and this is also given in the exams. So you have this table. So not only do you have the differential ones that we were using before, but you also have the unit vectors for cylindrical and spherical coordinates. So now we are interested in e rho hat, which is this one here. Let me scroll up, this one here, okay? So e rho hat is cosine phi x hat plus sine phi y hat. So this is cosine phi x hat plus sine phi y hat. So at this point, if you have done many dot products, you might be able to realize that since only x hat dot x hat will be 1 and y hat dot y hat will be 1, all the other combinations will be 0, you might directly be able to write the answer as yz times cosine times r plus xz times sine times r. And that would be correct. But since this is the first time I'm doing a problem with the dot product in the Flux, let me do it explicitly. Okay, so let me explicitly expand this first term. Dot r cosine phi x hat plus r sine phi y hat. So I multiplied the r and then I keep dz and d phi outside. Okay, I moved dz d phi outside and multiplied r by this parenthesis. So now we have to multiply out these two brackets. So we will get lots of combinations. So we will get yz r cosine phi x hat dot x hat. Then we will get this times this x hat dot y hat. So it will be this times this x hat dot y hat. But this will be 0. So I don't bother writing it out. Okay. Plus, now we have to go to the next term. So we get this times this. So that will be something with y hat dot x hat, which will be 0. Then the next term will be this times this. So it will be x times z times r sine phi y hat dot y hat. And then the next term will be this times this z hat dot x hat. So it will be something z hat dot x hat, which will be 0. And finally, we'll have this term times this term. So we will have something times z hat dot y hat, which will be 0. So all these terms go to 0. Okay, so the only two terms that survive, and of course don't forget at the end we have dz d phi. So the only two terms that survive are these ones, where this is equal to 1. Okay? So if that is clear now, we will get y z r cosine phi times 1 plus x z r sine phi times 1 times dz times d phi. So we are done. Let's integrate, right? So we can do now the integral in z and phi. Wrong. Always do a sanity check at the end of step 3. Is this ready for integration? Is everything, either the two parameters z and phi, or constants? We have a r is a constant, we have phi, r, phi, z is fine, but we have a y and we have an x. We don't need a y and an x. We cannot have a y and an x, okay? We need to substitute, we need to evaluate the integrand at the surface. So this means that these arrows for f, they are changing as we move throughout the surface. So we need to evaluate what these arrows are at the surface, which means that we need to substitute. Remember that the parameterization of the surface is just x, y, and z. So wherever there is an x, I need to write this. And wherever there is a y, I need to write this. Okay? So let's do it. So this is r sine theta times z times r cosine theta plus r cosine theta times z times r sine theta dz d phi. Which actually these two terms are the same, so we get 2r squared z sine theta cosine theta. Okay? Times dz d phi. Very good. Now, is this ready to integrate now? Does it only have constants and the two parameters? Yes, the two parameters are z and phi, and we have them here. And then we only have r, which is a constant. So this is now ready to do the double integration. So now we go to the fourth and final step, perform the double integral. And maybe now you appreciate why I insist so much that this last step is the easy one. You really need to make sure that you made all of the previous 3 steps correctly. Okay? So now the flux is the double integral f dot ds, which is equal to the double integral of this thing, which is 2r squared z sine phi cosine phi dz d phi. So what are the limits? Z is the inner integral, and Z we said goes between 0 and h, and phi, that's the outer integral. The limits are going between 0 and 2 pi. We can apply separation of integrals because we have a function of Z times a function of phi. So they are multiplying each other, so we can apply separation of integrals, and we can take this constant outside. So you get that this is equal to 2r squared times the integral from 0 to h of z dz times the integral from 0 to 2 pi of sine phi cosine phi d phi. Okay? So the integral of this is just h squared divided by 2. And what is the integral of sine phi times cosine phi? Let me give you a trick for this. I don't recommend you start doing substitution. To be honest, I think this integral is easy enough that you should be able to do in your head by thinking backwards. So think about it. What is the derivative with respect to phi of sine of phi squared? So what is the derivative of that? So you know this will be equal to 2 times the derivative of what is inside the bracket, which will be cosine, times sine times the bracket, but subtracting 1 to the power. So you get 2 times cosine times sine. That is the derivative of sine squared. But that is almost exactly what you have here, except for the 2. So you just need to divide this by 2. Okay? So, or even if we move this 2 that is outside The 2 that was here, we put it inside. So now this is even easier. So now this is just, the integral of this is just sine squared of phi between 0 and 2 pi. Okay. Now it turns out that sine squared of 2 pi is 0, minus sine squared of 0 is also 0. So the answer to this is 0, which means that our total flux turns out to be 0. Okay? Let me talk about the meaning of why a flux can be 0. And the fact is that if at some points on the surface the flux is going out, but at other points in the surface the flux or the vector field is going in, so it seems that in this problem the flux going out exactly cancels out the flux going in. And when you calculate the total flux, you are calculating the net flux. So if at some points it's going in and if at some points it's going out, and they exactly cancel out, you get 0, which is what we got in this problem. Okay? And that's it. So that's a calculation of a flux integral, which was quite complex, but you see that if you follow the steps one by one, it's not difficult. Okay? You have plenty of many more problems in the problem sheets, in the PDF notes. Okay, thank you very much for watching. See you in the next chapter.